Bismillahirrahmanirrahim. Assalamu alaikum. I'm Fatma Sherilyn. Welcome to Telekilaas A-Level Chemistry. Today I'll be going to look at calculations in IAS Chemistry. Unit 1, Formulae, equations and amount of substance. So the major parts that are covered in this session will be, first one, mathematical skills in IAS and IAL chemistry, mole, calculations using reactive masses, limiting and excess reagents, percentage yield and atom economy. Mathematical skills in IAS and IAL chemistry. Actually, I'm going to look at some of the areas that are covered in this specification of Edexcel. Now, there are 5 important aspects that you need to acquire within the 2 years of study. First one, arithmetic and numerical computations, graphs, handling data, algebra, geometry and trigonometry. Under arithmetic computations, you need to actually be familiar with the appropriate units in calculation, decimals and ordinary form, be able to use ratios, fractions and percentages, make estimates of results of calculation. Now, in this part, you will be familiar about the ionization energies that you have studied. In some questions, you will be required to give values without doing any calculations or approximations. Use calculators to find and use power, exponential and logarithmic functions. Mainly this part will be covered in Unit 4 of Edexcel chemistry. Handling data, use of appropriate number of significant figures, finding arithmetic means. Now, in using significant figures, you should never give your answer to 1 decimal place. At least 3 to 4 significant figures must be given in your answer. Find arithmetic means. Actually, you are familiar with titrations in grade 10, which you will be doing it in A-level chemistry as well. So, finding the mean titer is one of those examples here. Identify uncertainties in measurements and use simple techniques to determine uncertainty when data are combined. Now, in this part, we will be actually talking about finding percentage error of different instruments. Let's say, for example, if you are measuring a mass of substance, the percentage error that inquires in finding the mass will be taken into account, or if you are measuring volume using a pipette or a burette, the percentage error that goes on in the measuring of the volume will also be considered here. Algebra, this is actually dealing with grade 10 chemistry. So, you should be able to familiarize with these signs, including equilibrium sign. So, equilibrium means those reactions that go in the forward and backward reaction. So, this is one of those signs which you have to be familiar with. Change the subject of an equation, substitute numerical values into algebraic equation using appropriate units for physical quantities. Solve algebraic equations. Use logarithms in relation to quantities that range over several orders of magnitude. Now, this part will be seen in Unit 1 in ionization energy graphs. Some values are taken as log of those values because you are dealing with very, very large numbers here. And mainly the calculations using logarithms will be seen in Unit 4 of A-level chemistry. Graphs. You should be able to translate information between graphical and numerical algebraic forms. So, if a graph is given, you should be able to read through the graph and take the information from the graph in answering the questions. Plot two variables, an experiment or other data. So, if a set of data is given, you should be able to plot the graph and then draw them and take information from the graph. Determine the slope and intercept of a linear graph, calculate rate of change from graph showing a linear relationship, draw and use slope of a tangent to a curve as measure of rate of change. Actually, again, a very large proportion of the calculations will be done in Unit 4. So, under kinetics, you will be seeing these 2 points being covered. Geometric and trigonometry, here we are not talking about mathematics, but it will be taught in the context of chemistry. So, geometry and trigonometry will be dealing with 2D and 3D structures of different molecules, the bond angles, the shapes of different molecules, Visualize and represent 2D and 3D forms, including two-dimensional representations of 3D objects. You have already seen in bonding under shapes of molecules, the bond angles and different shapes of molecules. In addition to that, we will also be looking at organic chemistry isomers, and under this you have gone through the section on geometric isomers, that is cis and trans, EZ isomers. In Unit 4, you will also be looking at optical isomers, which is also based on its 2D structure. Understand the symmetry of 2D and 3D shapes. So, what are the, how much of the mathematical skills are assessed in your papers? In Unit 1, there is 18 marks allocated for calculations. Unit 2, 18 marks, and Unit 3, it's about 6 marks of the overall work that is being covered. So, in Unit 1 and 2, about 22% of the assessment will be covering calculations related to chemistry. Second one, mole. So, mole, what do we mean by a mole? So, let's have a look at some of the real life examples of mole. Now, if I say a pair of shoes, what comes to your mind? A pair means 2 shoes. Now, if I say a dozen of eggs, we are talking about 12 eggs. If I say a team of football players, then I am talking about 11 players. So, a team of football players have 11 people in it. Now, what do we mean by mole? Right? A mole means a specific number of particles, like a pair of shoes, a dozen of eggs, or a team of football players. And it is 6.02 into 10 to the power 23 things. In chemistry, we call them particles. So, in 1 mole, we are talking about 6.02 into 10 to the power 23 particles, and mole is the unit that is used to measure the amount of substance that is present. Now, this is Avogadro. This number is also known as the Avogadro's constant. Avogadro is an Italian scientist who actually introduced the scaling up factor for atoms, molecules, and ions to mass, that is in terms of grams. Now, why are we talking about moles and why is moles so important? Now, moles is important because moles can be converted into various forms. Moles can be converted into grams, that is in terms of mass. Moles can be expressed in terms of number of particles, and moles can be expressed in terms of volume of gas. So, if you keep this slide in mind, it will be really easy for your calculations. Now, if you want to convert moles to mass, moles need to be multiplied by the molar mass or atomic mass in order to find the mass of the substance. If you want to go back mass to moles, mass needs to be divided by the molar mass or atomic mass in order to find the number of moles. Similarly, if you want to convert moles to volume, moles can be multiplied by 24 dm cube to convert it into volume of gas, and volume of gas needs to be divided by 24 dm cube in order to work out the number of moles of substance. If you are talking in terms of number of particles and moles, moles can be converted to particles by multiplying moles by 6 into 10 to the power 23. And if you want to go back from number of particles to moles, number of particles must be divided by 6 into 10 to the power 23 to find the moles. Now, when dealing with substances, you have to be careful, especially talking about moles of substance and mass. So, the relationship that you need to remember here is moles is equal to mass over molar mass. So, molar mass depends on whether you are going to use an element or a sub-element or a compound. So, if it is an element, the molar mass will be the relative atomic mass. If it is a molecule or a compound, it will be relative molecular mass. Relationship between moles and volume. Now, in this one, the volume is applied only for gases. So, if you are using a solution, you cannot use this relationship 1 mole of any gas equals 24 dm cube, because it must be always the number of moles of gas that will occupy that volume. So it can be either expressed as dm cube or centimeter cube. 1 mole is 24 dm cube or 1 mole is 24,000 centimeter cube. The conversion factor here is 1 dm cube is equal to 1000 centimeter cube. The relationship between number of particles is, as we have seen in the previous slide, 1 mole of any substance is 6 into 10 to the 6.02 into 10 to the power 23 particles. Now let us have a look at a question here. Sodium chloride can be made by reacting sodium with chlorine. So that's the stoichiometric equation. Stoichiometric equation means the balanced equation for the reaction. Calculate the volume of chlorine gas required to react with 92 grams of sodium. So volume of chlorine gas and you are given the mass of sodium. How do we work this out? The traditional way of doing this is actually initially find the moles of 92 grams of sodium. So it is done here, mass over molar mass, 92 over 23 giving 4 moles of sodium, and then from there you can actually go back to the equation because we need to find the relationship between the reactive masses of sodium and chlorine. So sodium and chlorine reacts in 2:1 ratio. So 2 moles react with 1 mole of chlorine. So we have got 4 moles of sodium reacting with how much? And the answer is 2. So once you get the number of moles, you can use the relationship where 1 mole of any gas occupies 24 dm cube and then find the volume for 2 moles, which is 48. A simpler way of doing this is, this is a straightaway method where you can actually use, now because you are given mass and volume, you can simply use the mass of sodium and then volume of chlorine on this side. So from the equation, the first statement is written from the equation. So 2 moles of sodium, so 2 times 23. It is really handy to have a periodic table with you when doing these calculations because these values that are taken, the relative atomic masses are taken from the periodic table. So 2 times 23 for this, and then chlorine 1 into 24 dm cube because we have 1 mole of chlorine gas here. So we can check 92 will be taking up how much of chlorine. So both these calculation gives the same answer, but this is a far simpler method of doing it and also you will be saving a lot of time. Next one is calculations based on reactive masses. Now for doing these calculations, it is important that you have a balanced equation, chemical equation, and it provides a lot of information about the reaction that occurs between the 2 reactants and the amount of products. So provides information about the relative proportions of reactants and products in terms of moles. The amount of moles involved can be scaled up or down, but the ratio must remain the same. So looking at this equation, the information that is given here can be expressed in terms of moles, molecules, or amount of substance in grams. But if you look at the total amount of products and reactants on both sides, you will find that on the reactant side we have 4 plus 32, which is 36, and also on the product side we have the same mass of substance present. So, and one example here in terms of reactive masses, calculate the mass of aluminium oxide produced if 6 moles of aluminium react with excess oxygen. Very important here to note that we have oxygen in excess. In any of the calculations that you do, excess will not be used in the calculation because it is always the limiting reagent that will decide the total amount of product that will be formed. So in this one, 6 moles of aluminium will be the limiting reagent, and then you can work out the amount of aluminium oxide present. So from the equation, because we are dealing with stoichiometric equations, 4 moles of aluminium produces 2 moles of aluminium oxide. We need mass of aluminium oxide. So 4 moles reacting with giving 2 moles of aluminium oxide. So question says 6 moles of aluminium will give us how much? And when you work it out, you will be getting 3 moles for that. And then there is a step 2 because your final answer must be given as mass of substance. So, moles and mass is related by the expression moles is mass over molar mass, and mass can be made the subject in this equation, and when you do this you have to actually work out the molar mass of aluminium oxide. So, aluminium oxide has 2 aluminium atoms and 3 oxygen atoms. So, 2 times 27 is the molecular mass, atomic mass of aluminium. 3 times 16 is the atomic mass of oxygen. So, the total molar mass is 102. When you work it out, 3 times 102, 3 moles into 102 gives us 306 grams for this question. Now, another example involving gases. The equation for the complete combustion of ethene is given here. What volume of oxygen gas is required to completely burn 50 centimeter cube of ethene? Now, you need to work out which one is ethene here. So, this is ethene and that is oxygen, right. So, when reacting, ethene, 1 mole of ethene reacts with 3 moles of oxygen. So, if you remember from the previous slides, 1 mole of any gas will occupy 24,000 centimeter cube. So, if it is 3 moles, you need to multiply 3 by 24,000 to get the total volume of this 3 moles of oxygen. So, here we are asked to work out the amount that is required to react with 50 will give us how much. So, when you work it out, the answer for this question is 150 centimeter cube. So, as I have mentioned earlier, limiting and excess reagents are very important in chemistry. So, let us have a look at a real life example that we come across every day. How many hot dog in a bun can be made? I have got 5 hot dogs and 4 buns. So, the total amount of hot dogs that I can make here will be 4 hot dogs in bun, and then I will have 1 leftover hot dog from here, right. So, what does this tell us? Now, we have 5 hot dogs and 4 buns here, and the total amount of hot dog in buns I have got is 4. So, the amount of product that we get always depends on the limiting reagent. The excess will remain as it is. So, in every calculation, limiting reagent is important because it will give us the total amount of product that will be produced in any chemical reaction. So, that is the theoretical yield and that is the excess reagent. So, in chemistry, a limiting reagent is a substance that is completely used up in the reaction, and that will give the reactant limits the amount of product that is formed, and also the reaction will stop as soon as the limiting reagent is used up. But on the other hand, the excess reagent will be the one that is in excess, and then there will be always some extra at the end of the reaction. Now, deciding which reactants are limiting and excess in any reaction, you need to follow these few steps in order to work it out. So, first thing is write a balanced equation. Majority of the time the balanced equation will be given in question. So, calculate the available moles for each reactant, determine the mole ratios of reactants from balanced equations, and once you get that, you can compare the amount that you have obtained with the given amount that is in question, and then see if any of it is in excess or limiting. Now, just an example here. Consider the reaction below: 2 nitrogen monoxide reacting with oxygen to form 2 moles of nitrogen dioxide. What is the maximum volume in dm cube of nitrogen dioxide that could be obtained in the reaction occurring when 1 dm cube of nitrogen reacts with 2 dm cubes of oxygen? Now, in this question, it does not tell us to work out the limiting reagent, but you should be able to work it for yourself, that here you are given 2 amounts of 2 reactants, and so you have to know which one is the limiting reagent, right. It does not say which one is limiting. So, the first step that you need to work out is, even though the question does not talk about limiting or excess calculation, you have to do the calculation. So finding the limiting reagent. According to the equation, 2 moles react with 1 mole of oxygen. So 2 moles react with 1 mole. In terms of volume, if we take 2 moles will occupy 24 dm cube and 1 mole will occupy 2 moles will occupy 2 times 24 dm cube, 1 mole will occupy 24. So 1 dm cube will be X. If you look at it, we are getting 0.5 dm cubes of oxygen, right? And 0.5 dm cubes is how much we require, but we have 2 dm cube of oxygen in question. So what does that mean? We are talking about oxygen gas that is in excess. Actually, for these calculations, you can either take the nitrogen to do the calculation, or you can choose the amount of oxygen for the calculation. So it doesn't make any difference there. You'll be able to still work out the limiting and excess reagent there. Now once you get the limiting reagent and excess worked out, you can do the second step, which is finding the answer for this question. So what is the maximum volume of nitrogen dioxide? Your calculation must be based on the limiting reagent. So here limiting reagent is nitrogen monoxide, and then that is the product. So 2 moles of nitrogen monoxide giving 2 moles of nitrogen dioxide. They are in equal, they are actually producing equal number of moles in reaction. So if you do it in terms of volume, here it will be occupying 2 into 24, and there it will be occupying 2 into 24. In other words, it's a very straightforward calculation. So 1 dm cube will definitely be giving a volume of 1 dm cube. So answer here is A, which is 1 dm cube for that question. Now this is a multiple choice question. You have to be very careful. In A level there are 20 multiple choice questions to start with, but some of these calculations take up more time than you think. So you have to actually do it in a method that actually takes up the least amount of time. Percentage yield. Percentage yield is a method that is used to check the efficiency of the chemical process. So mainly the percentage yield will be dealing with the amount of product that you get at the end of the process. It will not consider the amount of waste that is produced or amount of raw materials that is used up in any of these chemical reactions. So in percentage yield there are 2 key terms that you have to know. They are the theoretical yield and the percentage yield, the actual yield. Theoretical yield is the maximum mass that you expect from any chemical reaction based on its stoichiometric equation. Actual yield is actually the amount that you obtain from experiment or from the process. So this equation is important. Percentage yield giving actual yield over theoretical yield into 100. In most calculations, the actual yield will be given to you, and then you will have to work out the theoretical yield for that calculation. So now you need to know that actual yield is always less than the theoretical yield, because theoretical yield is how much that you are expecting in theory, right? The experimental yield is actually low because of few reasons. Number one, the reaction may be reversible and it may not have gone to completion, or there can be side reactions taking place. Due to that, there can be other products formed in the reaction, or the substance may need to be purified, and so during the purification process you might be losing some of the product, or it could be that there can be transfer losses where during filtration or when you are changing from one container to the other, and for these few reasons, for those reasons the actual yield is actually less than the theoretical yield. A simple calculation on this percentage percentage yield calculations are very common in Edexcel question papers. So in this one we are looking at sodium carbonate being an important industrial chemical manufactured by Solvay process, and the equation is given. So this reaction we are using 75 kilograms of calcium carbonate, and then we are obtaining 76.5 kilograms of sodium carbonate. Calculate the percentage yield for this reaction. So manufacturer is using 75 kilograms of calcium carbonate to make 76.5 kilograms of sodium carbonate. That's the yield of the reaction, and that's the reactant that we are using. So in this calculation, we need to initially work out the theoretical yield, and to do that we have calcium carbonate and sodium carbonate in question. So in this one I have taken the masses directly from the equation. So working out the amount of calcium carbonate, calcium from the periodic table is 40 plus 12 plus 16 times 3, because there are 3 atoms of oxygen, that gives us 100.1 kilogram. On the other hand, we have sodium carbonate. You do the same, work out the relative molecular mass, and we get 106 kilograms. So 75 kilograms of calcium carbonate will produce how much? Now in this one I am using kilograms because it's a ratio and proportion where we are using the same units. Step 2, calculate the percentage yield. Percentage yield is actual over theoretical into 100. So the actual is the amount given in question, which is 76.5, and the theoretical yield that you have calculated is 79.4 multiplied by 100. So we are getting a percentage yield of 96.3%. So that means that's quite a high yield, and this process is actually an efficient process to produce sodium carbonate. Atom economy. Atom economy is also a method to work out the efficiency of chemical reactions, and this actually takes into consideration the amount of waste that is produced in reactions. So in atom economy, it's an alternative way to assess the efficiency of reactions, and we check the amount of useful product, the atoms that end up in the useful product, and atom economy is given as molecular mass of desired product over sum of molecular masses of all products into 100. So a simple calculation in this one, we have hydrogen as the desired product. So in working out the calculation, we have atom economy, molecular mass of desired product over the total mass of all products. Atom economy, calculate the mass here, 4 times 1, and mass of carbon dioxide, mass of hydrogen, all added together. And in this process, we are getting a percentage of 8.33% as atom economy. So if you think of the process, the efficiency of process, this cannot be considered as an efficient process because we have a very low amount of atoms ending up in the desired product. And you might be coming across this type of questions as well, where you are given 2 processes and then you are asked to work out the percentage, the atom economy of the process without doing any calculation. So by looking at the question, you should be able to work out. Now how you do that is, if you look at these 2 processes, we are producing phosphoric acid in the reaction. So in this process, the phosphoric acid is prepared by reacting with calcium phosphate and sulfuric acid in the first one, and in the second one, phosphorus, oxygen and water put together to give phosphoric acid. Now if you look at the second process, you can see that all of the reactive molecules or atoms that are in the reactants are ending up in the useful product. So there is no waste produced in this reaction. So we know that this reaction, even without any calculation, produces a atom economy of 100%. But if you look at the first one, along with phosphoric acid, it is also producing some amount of calcium sulfate as a waste product. So here we can say that the atom economy is less than 100 without doing any calculation. So to generalize, you can say that in all addition reactions, they have a 100% atom economy, because addition reactions will give in one single product at the end of the reaction. But substitution reactions, like you are seeing here, substitution actually gives up gives in two different products for the reaction, one being the desired product and the other one being the waste product. So, these reactions will be producing atom economy which is less than 100%. So, in summary, we have actually looked into mathematical skills in IAL, mole, calculations using reactive masses, limiting and excess reagents, percentage yield and atom economy. So, I hope this has been a useful session for you. Thank you very much.